Hello, this is the last video that I have to make as far as content goes, and I have to fly out back to Indianapolis in a couple hours, so we'll see. As long as this doesn't take over 2 hours, I think we will be good, but it's going to be a long one. This is cylindrical integration, so it can get a little sketchy. And in general, everything we're going to need for cylindrical integration is that, let's see, x squared plus y squared is equal to r squared. Oops. X squared plus y squared is equal to r squared. Also, x is equal to r cosine theta. Y is equal to r sine theta. And really, we'll be able to get by with this. We also have to note that our base cylindrical integral over our region, over our volume E, will be expressed as dz r dr d theta. So pretty much all that means is that we have to remember that there will always be an r sitting in our integrand before we get to it ourselves. So our first integral and our integrand is going to become dz, and that z is going to stay the same because in cylindrical coordinates z is just z, but our bounds are going to change. This is going to become root 3r, and on top we're going to get root 8 minus r squared, and then in our integrand we're going to get r to the fourth sine squared theta cosine theta. And then just taking a look at our last two integrals, we see that this is going to be graphing out the xy shadow of our region, which is going to be the bounded on top by the top half semicircle of radius root 2, and on the bottom by the reflection over the x-axis of that same semicircle, where x is running from 0 up to root 2. So we're dealing with this region in here, and we can use that to set up our other bounds. dr d theta, where r is going to run from 0 to root 2, and theta runs from negative pi over 2 to pi over 2. So we can find our answer here as answer choice C. Let's find the volume of the region below this graph and above this graph. First of all, let's convert these into cylindrical coordinates. This will be z equals 16 minus r squared, and here we will get z equals 3r squared. And we're going to have to figure out our intersections between these. This is going to be a downward opening paraboloid, so something like that. And then here we're going to have an upward opening paraboloid. And there will be some value of z where both of these guys intersect, and we're going to need to know that. And so we can do that just by setting these equal to each other. We will find that 4r squared is equal to 16, or r is 2. Remember, we can't have a negative r because that's our radius, and it doesn't make much sense to have a negative radius. So we should have everything that we need to solve this. We can set up our three integrals. We know that we want all of our solids, so from 0 to 2 pi, we're not bounded anywhere on theta. What about r? Well, it looks like r is running from 0 to 2, like we found here, and z is running from 3r squared to 16 minus r squared, because they say that we're bounded on top by this thing and on the bottom by that. And then our integral is our integrand is going to be r dz dr d theta. And we can evaluate this. So there are no z's in this integrand, so we're just going to multiply this in and subtract and multiply that in, and that's going to leave us with 16r minus 4r cubed dr d theta, which we can evaluate to 8r squared minus r to the fourth on 0 to 2, which will be 32 minus 16, or just 16. And so we're left with the integral from 0 to 2 pi of 16 d theta, which will be 32 pi. Let's convert this integral into cylindrical coordinates and then evaluate it. Just like before, we're going to take a look at this guy over here and then move out to our other integrals. So converting our dz into our dz integral into cylindrical, you'll see that it's bounded on 0 to 4 minus r squared, and then we're going to have 15 r squared dz as our integrand. And now moving out, we're going to graph this guy. We see that we're bounded on the bottom by y equals 0, and on the top by the semicircle of radius 2. And then we see that x runs from -2 to 2, so we're dealing with this whole region in here. So dr runs from 0 to 2, and d theta runs from 0 to pi. It's a bad pi, but whatever, they're all bad. Okay, so yet again we have no z in this integral, so we're just going to multiply 4 minus r squared in, and we're going to get, actually, I already forgot what it was. Okay, we're going to get the integral from 0 to 2, integral from 0 to pi of 60 r squared minus 15 r to the 4th dr d theta. Also, we have no thetas to worry about, so we can just move a pi out here. So now, integrating, we're going to get 20 r cubed minus 3 r to the 5th on 0 to 2. This will give us, well, 20 times 8 minus 3 times 32, which is going to be 160 minus 96. And this is going to give us 64, which multiplied by the pi that we had sitting out here will give us our 64 pi, which is our answer. Okay, which of the following integrals represent the volume of the solid enclosed by these two things right here? So this is going to be the sphere of radius root 2 and the cone, just like the normal cone. They haven't done anything weird to this thing. So we know that for our dz integral, we want these in terms of z equals, and this guy already has it, so we're going to be bounded on the bottom by z equals r, converting this thing. And you can kind of see this if we draw it out, we're going to have this cone coming out to meet the radius of the sphere, and then the sphere is going to take over. This is our classic snow cone shape that they make us integrate over sometimes. And so we can take this guy over here and convert it into z equals by saying z equals the square root of 2 minus x squared minus y squared, or just z equals root 2 minus r squared. And that will be the top bound on our dz integral. So looking for that in our answer choices, we see that we can cross out D and E, and we're left with A, B, and C. Okay, what is our bound on R going to be? Well, for Z equals, if we draw our Z, oh god, that's bad. If we draw our Z axis through here at Z equals 0, since we're dealing with a cone, R also equals 0, and we can evaluate that here to prove it. But what about at this this intersection point, which is going to be our widest point? That is going to be the intersection of these two, so we can set them equal to each other. R equals root 2 minus r squared, or r squared equals 2 minus r squared, which is 2r squared equals 2, or r equals 1. And so we should be our maximum r value coming off of our z-axis here should be 1. So our bounds on r are 0 to 1, and A is our correct answer. It might be tempting to kind of draw out your r's like this. You'll always get root 2 if you do, but remember that really isn't r in cylindrical coordinates. That's rho in spherical coordinates. And it's kind of confusing when they're giving us a sphere to deal with in cylindrical coordinates, but it'll be okay. Okay, moving on, we're told that a solid material occupies the region enclosed by the cylinder of radius 2 and some planes. And we're given its density, which is y squared, and we're told to find an integral that equals its mass. We know that we can convert this density function into cylindrical coordinates. This will just be r squared sine squared theta. And that in our integral already, there'll be sitting an r. So our integrand is going to be r cubed sine squared theta, which we can look for. And we see that in only a and c, so we're already down to a 50-50 here. And okay, let's figure out our bounds on z. We're bounded by z equals 0 on the bottom, and this thing in terms of z on the top, this will just be z equals 8 minus x, or z equals 8 minus r cosine theta, which we only see in answer choice D, which is our correct answer. Let's rewrite this integral in cylindrical coordinates. Well, doing what we usually do and taking our dz first, and then and our integral and our integrand, and then taking a look at dx dy later, we can turn these bounds into r and root 8 minus r squared, and our integrand is going to become r squared dz. And then as for our dr d theta, we just have to graph it. We see that we're bounded on x by the upper semicircle along the y-axis like that. We see that y runs from 0 to 2. So we're going to deal with this region right here. And so we can set that up in terms of dr d theta from r, with r from 0 to 2, and theta from 0 to pi over 2, which is going to be our answer choice A. Let's let E be the region bounded above by this paraboloid, which we can express as z equals 2 minus r squared, and below by the cone z equals r. And we're told to figure out which integral arises if we evaluate that thing using cylindrical coordinates. Well, we're not bounded on theta at all, so instead of setting up that integral, we'll just put a 2 pi outside of everything. We know that, let's see, our z is bounded on top by 2 minus r squared, and on the bottom by r. And our integrand is given right here. It's going to be z r cubed dz dr. And of course it's r cubed in here. We get an r squared from this guy, and then there'll already be an r in our integrand. Now as for our bounds on r, we are going to get our minimum r from our lower bound over here. When z is equal to 0, r is equal to 0. And we will get our maximum from setting these guys equal to each other and solving. So we will see that r squared minus, we have r equals 2 minus r squared, or r squared plus r minus 2 is equal to 0, and this factors to r plus 2, r minus 1. And the only positive root that we have here is r equals 1. And so evaluating, all they want us to do is evaluate this first step, because they have everything in terms of dr for our answer choices. And this will be z squared over 2 r cubed on r to 2 minus r squared, which is going to give us r cubed times 4 minus 4r squared plus r to the fourth over 2. And over here, we're going to get r cubed times r squared over 2. And so, taking a look at our answer choices, it looks like what they've done is taken this over 2 and just taken it completely out and divided our 2 pi by it. And answer choice D is identical to what we've already found. We have our integral from 0 to 1 multiplied by pi, bringing that half out of quantity 2 minus r squared times r cubed dr. Let's let E be the solid region bounded by the two surfaces whose equations in cylindrical coordinates are these guys. And we're told to find the volume of E. So we can set this up as a triple integral, even though we know that it's really a double integral with 2 pi sitting outside. We're not bounded on theta at all. And when z is equal to 0, we'll be able to tell which one of these is the upper surface and which is the lower surface. When r is equal to 0. So when r is equal to 0, this is z equals 10, and over here we have z equals 2. And that tells you that this guy, whichever one with the larger constant, which is right here in this case, is going to be on top. So 10 minus r squared, 2 plus r squared, dz. And then we know that our r is going to be bounded on top by the r value that the intersection of these guys produces. And that's going to give us, if we set these equal to each other, 10 minus r squared equals 2 plus r squared. That's going to give us 8 equals 2r squared, or r equals 2. And now we are ready to solve, except we almost forgot there's an r sitting in this integrand already. And so evaluating, since we have no z in here, this integral's going to get pretty easy. We're just going to end up with the integral from 0 to 2 times 2 pi of 10r minus r cubed minus 2r minus r cubed, which will give us 8r minus 2r cubed dr, which is 4r squared minus r to the fourth over 2 on 0 to 2, which is going to give us 16 minus 8, or 8 multiplied by our 2 pi. So we get an answer of 16 pi. Let's evaluate this triple integral where it's bounded by z equals, that's an r, 2 minus r squared, and z equals 1. So using the method that we used last time, we know that z, or our upper bound on z, will be the z with the larger constant in it. So we can set that. We can set up our entire integral. We know we're not bounded on theta at all, so we have a 2 pi out here. Our lower bound on z is 1. Our upper bound is 2 minus r squared, and r dz dr. We also have a 2z in here, so we can stick that in, 2z. And we know that our upper bound on r is going to be the intersection between these two, which is just going to give 1 equals 2 minus r squared, or r equals 1. And there we go, we're ready to evaluate our first integral. I'm actually going to move this r into here for now. So our first integral is going to give us z squared evaluated on 1 to 2 minus r squared, which will give us 4 minus 4r squared plus r to the fourth, and 1. So this will all evaluate to give us an integral from 0 to 1 of 3r. Remember, we got this r here that we have to multiply in. 3r minus 4r cubed plus r to the fifth dr. And I'll erase this to give us a little bit more room. This will be 3/2 r squared minus r to the 4th plus 1/6 r to the 6th, evaluated on 0 to 1. This will give us 3/2 minus 1 plus 1/6, which is just going to be, if we convert this into sixths, we will get minus 6 over 6 and 9 over 6. So 9 minus 6 plus 1 is 4 over 6, and we have to multiply by our 2 pi out here, which will give us 4 pi over 3, which is our answer. Okay, the equation of the surface phi, you know what? I think I've definitely totally been saying phi wrong this entire time, but just to bug some of you, I guess I'll switch now. So in literally the last content video that I'm doing, so phi is equal to pi over 4. We're converting that to cylindrical coordinates. So we know that if phi is pi over 4, this is just going to give us our cone that makes a 45-degree angle with both the x and the x-axis and the y-x plane, and this is just going to be, a normal cone. And we can express this in cylindrical coordinates, this cone, as z equals root x squared plus y squared, or just z equals r. And there's our answer. I think there is another way to do this one, where I'm pretty sure it uses like the tangent of something to get something else, but in the end I like doing it this way. I like graphing it out and thinking about it. If it's, let's say we were given, I don't know, pi over 6, we could do this in a similar way. This pi over 6 would just make an angle of 30 here and 60 here. And if we think about this in terms of the unit circle, that's going to be root 3 over 2 and 1/2 as our coordinates if we're just trying to figure out our slope, which is pretty much what we're looking for here. For every unit z that we go up, how many units r do we go out? And in the case of this guy, our slope is just going to be our rise over run, which will work out to 1/2 times 2 over root 3, or just 1 over root 3. And so that's just an example. You can use this method, kind of looking at unit circle things and graphing things out, to make any of these given surfaces work. Wow, this is the last question that I have to do. I probably will do more, but this feels very weird to me. We're converting this into cylindrical coordinates, and let's try to do it nice and fast. So our integrand is going to become 8r cubed dz. Our bounds on z are 0 and r. And if we graph out this region, we see that we're bounded on the top by the hemisphere of radius 3, and x runs from -3 to 3. So we're dealing with this entire region here. R runs from 0 to 3, like we saw with that hemisphere, and theta runs from 0 to pi. And there's our integral, and we can just cross off everything that doesn't match. And then we are done. Hope this was helpful. Actually, it wasn't as bad as I expected it to be. A lot of cylindrical integration gets pretty monotonous, and just plug and chug, make a big polynomial, integrate it, and we're good. Thanks for tuning in.